Hi everyone. For my paper, I chose liquid level sensing using commodity Wi-Fi in a smart home environment. So the motivation for this is that tracking consumption, expiration notification, and automatic reordering is desirable for both consumers and healthcare. And Wi-Fi can be used to detect and monitor liquids in containers to perform these operations. Current solutions are either too expensive, don't scale, or unsuitable for a home environment. Some of these other solutions are a capacitance-based model, which uses a submerged sensor, which may contaminate the liquid, to measure capacitance of the entire container, which changes with liquid level since the liquid is a dielectric. Another solution can be a wrapped sensor, so as to not contaminate the liquid, but needs specifically designed hardware and additional communication hardware, which makes it expensive and non-scalable. A pressure-based model uses a pressure sensor attached to the bottom of the container to track pressure changes over time. This will also require additional communication hardware to interact with the smart home network. The paper also described several camera-based applications which used learning algorithms like multi-layer perceptron networks, k-nearest neighbors, or convolutional neural networks to measure food or waste bin levels. This wasn't shown to be used with liquids, but it would require transparent containers and opaque liquids. An acoustic model basically measures the time of flight through the container. So extra hardware would have to be put in, and again needs additional hardware to communicate with the smart home network. A vibration-based model uses specialized polyvinylidene fluoride sensor mounted on the side of a container, which when receiving a excitation generates a vibration, and the sensor measures the resonance frequency, which can be used to predict only discrete fill levels, not continuously predict. Finally, a radio frequency-based application senses the level and type of liquid. There are many applications and methods, but these are mainly used for identification and require hardware that is not available in a household setting, like a Doppler sensor and piezoelectric vibrator, or use electrodes on either side of the container. So to summarize, some challenges and limitations of these previous solutions are cost, line of sight, integration, accuracy, and scale. Therefore, a solution must be relatively cheap, not depend on line of sight, be easily integratable into a home network, and scalable, and of course have a high degree of accuracy and reliability. So here's some background information which will be necessary moving forward. So everything has a natural frequency that it vibrates at. Resonance is the maximum amplitude created by an addition of a same frequency vibration to the system. Resonance varies with mass, which is directly related to liquid level. Additionally, 5 GHz Wi-Fi, which is found in most homes, can detect millimeter level vibrations. Since the disturbances from these liquid vibrations is about 2 to 3 millimeters, Wi-Fi can be used to detect these vibrations with a high accuracy. Most signals and inputs have redundancies that only increase computational overhead. PCA selects only the most important parts of a signal, which have the greatest impact on analysis, thereby reducing dimensionality. And finally, frequency domain analysis uses methods like Fourier transforms to break down a signal into its components. So here's an overview of the system. Basically, a low-cost transducer is attached to the outside of a container. It emits a signal, which makes the container vibrate at a resonance frequency, thereby disturbing the Wi-Fi signals around it. Smart devices can detect the differences in these Wi-Fi signals and either analyze it on the device or send it to a backend server for more functionality. As we can see in this graph, frequency and liquid level are negatively correlated. That is, at higher liquid levels, the frequency goes down. And we can see here that between around 800 and 1800 milliliters, the relationship is linear, while at lower levels, the relationship is a cubic polynomial. Here's the same graph, just flipped. and it shows the differences between thick and thin liquids. As we can see, there isn't much of a difference. They both follow the same general curve and have the same intercept points. So as we can see here, this is the system flow. First, a device chirps, making the container resonate. This disturbs the Wi-Fi signals around it. Then, using commodity Wi-Fi, it probes for the container, and extracts CSI information from the receiver. And CSI is basically the channel state information, which describes signal changes through the physical space. Next, we pass this information through data processing to take out noise and phase shifts between the transmitter and receiver. And then we extract features using PCA and extract the resonance frequency using frequency domain analysis. Finally, they predict the level using either a discrete or continuous method. The discrete uses a support vector machine, while the continuous uses curve fitting to train a model. Then that model is used for continuous predictions. The contributions of this paper are that resonance frequency of a container of liquid can be used to indicate liquid level, and LiquidSense provides a low-cost, high-accuracy solution to detecting liquid levels using Wi-Fi. They got a 97% accuracy for continuous prediction and found that distance and angle or line of sight doesn't impact performance. So here's the setup for the performance evaluation. Basically, they had two laptops, one's a receiver, one's a transmitter. The receiver is connected to 3 antennas and the transmitter just has one. The container is placed between them with the transducer attached, and they tested on different container materials and sizes and different liquids like vegetable oil, water, Coke, milk, laundry detergent, and dishwashing liquid. They found a 97% accuracy in detecting the level of the liquid, and also found that 90% of their errors are lower than 6%, so they have a high degree of reliability. They showed that liquid thickness, container material, container size, and line of sight had no effect on accuracy, although they did show that an increase in distance did lower their accuracy. In conclusion, LiquidSense is a low-cost, cheap transducer, only costing a few dollars. It can attach to any container, making it easy to install and scalable. And because it only requires 5 GHz Wi-Fi, which is very common, it is immediately integratable into smart home networks. It has a high accuracy, irrespective of container or liquid, and line of sight has no impact because Wi-Fi reaches everywhere. Though it is negatively impacted by distance, this can become negligible by selecting smart home devices nearby to the container, and since we are assuming a smart home environment has many devices, we can always find nearby devices. The paper laid out some future work for their project. So the current system only tests one container. However, they theorized that with time division multiple access and frequency division multiple access, they could discriminate between dozens of containers, for example, in a restaurant or in a factory. Power consumption is another issue they saw, where sensing 3 to 5 times a day on a single cell only lasts a couple months. To remedy this, they can lower their frequency band from 1000 Hz to 250 Hz, and additionally combine it with motion detection to avoid redundant measurements, only measuring when the liquid is moved. The current model uses supervised learning for predictions, which requires labeled data, which can be expensive or hard to obtain. So unsupervised learning could help this, though the trade-off would be between training effort and model accuracy. Some additional applications that they laid out in the paper are consumer applications, so tracking consumption of certain liquids or monitoring the calories of households and automatically reordering certain supplies, stuff like that. Any questions?